Diagonal matrix. Hello everyone. Today, we are going to introduce a very important concept in linear algebra called the diagonal matrix. To begin, it is essential to understand that a diagonal matrix is a specialized type of square matrix. This means that for a matrix to even be considered for this category, it must have an equal number of rows and columns. Before we dive into the formal definition, we first need to be familiar with the concept of the main diagonal. If you look at any square matrix, the main diagonal is simply the path of elements that runs from the top left corner straight down to the bottom right corner. Now, in simple terms, we call a square matrix a diagonal matrix if every single element that is not located on this main diagonal is equal to 0. Over the next few slides, we will translate this simple idea into a formal mathematical definition, look at some visual representations, and explore how this is actually used in fields like computer graphics. Mathematical definition. Now that we have a general understanding of the main diagonal, let's move on to the formal mathematical definition. A square matrix, which we will call matrix B with dimensions m by m, is defined as a diagonal matrix if all of its non-diagonal elements are 0. To express this condition mathematically, we state that the element b sub ij equals 0 whenever I is not equal to j. To clarify this notation, the letter I represents the row index, and the letter j represents the column index. Therefore, the condition where I is not equal to j refers to every position in the matrix that does not fall on the main diagonal. It is important to note that the elements located on the main diagonal, which are the positions where I equals j, can be any value. These can be positive numbers, negative numbers, fractions, or even 0. In the next slide, we will look at a visual representation to see exactly how this definition looks in practice. Visual representation. Now that we have established the mathematical definition, let us look at a visual representation to solidify the concept. Consider a general 3x3 diagonal matrix, which we will call matrix D. As you can see in the matrix displayed, the elements D11, D22, and D33, which run from the top left corner down to the bottom right corner, are the diagonal elements. Crucially, every other position in the matrix, such as D12, D13, D21, D23, D31, and D32, is strictly 0. This visually demonstrates the condition we just discussed in the previous slide, that any element where the row index does not equal the column index must be 0. Real-world application, scaling in computer graphics. Now that we have established the mathematical definition and the visual structure of a diagonal matrix, you might be wondering how these are applied in the real world. While matrices can often seem like abstract arrays of numbers, diagonal matrices are actually used extensively in computer graphics, a process known as scaling. To help you visualize this, imagine you have a two-dimensional image on a screen and you want to stretch it to change its size. For example, if you want to double the width along the x-axis and triple the height along the y-axis, the computer utilizes a diagonal scaling matrix, which we will call matrix S. This matrix S is a 2x2 square matrix where the element in the first row, first column, is 2, and the element in the second row, second column, is 3, while all other non-diagonal elements are 0. By multiplying the coordinates of the image by this specific diagonal matrix, the system is able to scale the dimensions independently. This allows the image to be resized precisely without rotating it or distorting its shape, a process known as shearing. Having seen this practical application, let us now move forward to a step-by-step example to practice identifying these matrices ourselves. Step-by-step example. Now that we have covered the theoretical definition and seen how these matrices are used in computer graphics, let us apply this knowledge to a practical example. We will determine whether the given matrix A is a diagonal matrix. Matrix A consists of 3 rows and 3 columns, with the values 5, 0, and 0 in the first row, 0, -2, and 0 in the second row, and 0, 0, and 0 in the third row. To solve this, we will follow a systematic three-step process. Step 1. We must first check if the matrix is square. As we discussed in the introduction, a diagonal matrix must be square by definition. Looking at matrix A, we can see it has 3 rows and 3 columns. Because the number of rows equals the number of columns, it is confirmed to be a square matrix of order 3 by 3. Step 2. Next, we identify the non-diagonal elements. These are the elements where the row index I is not equal to the column index j. Let us list them specifically. The element at row 1, column 2 is 0, row 1, column 3 is 0, row 2, column 1 is 0, row 2, column 3 is 0, row 3, column 1 is 0, and row 3, column 2 is 0. Step 3. Now, we verify the condition. Since every single one of these non-diagonal elements is exactly 0, the mathematical condition that a sub ij equals 0 whenever I does not equal j is fully satisfied. In conclusion, because it is a square matrix and all elements outside the main diagonal are 0, matrix A is indeed a diagonal matrix. Note that the 0 appearing on the main diagonal at the bottom right does not disqualify it, as diagonal elements can be any value. Key takeaways. First, let's revisit the square requirement. As we established at the beginning, a matrix must be square, meaning the number of rows must be exactly equal to the number of columns to even be considered for the category of a diagonal matrix. Second, we have the 0 condition. This is the most critical rule. Every single element located outside the main diagonal must be 0. If even one element off the diagonal is a non-zero number, the matrix is no longer diagonal. Third, let's talk about diagonal flexibility. A common point of confusion is what happens on the main diagonal itself. Remember that the elements on the main diagonal can be any real number. They can be positive, negative, fractions, or even 0. There are no restrictions on these specific values. Finally, let's recap the formal notation. In mathematical terms, we express this entire condition as b sub ij equals 0. Whenever I is not equal to j, this is simply the shorthand way of saying that if the row index and the column index are different, the element at that position must be 0. Now that we have walked through the definition, the visual representation, and a practical example, let's consolidate everything into a few key takeaways to ensure you have a solid grasp of the concept. With these core principles in mind, let's move to the final slide, where we will discuss some common mistakes to avoid so you don't fall into the typical traps when solving these problems. Common mistakes to avoid. Now that we have covered the definition and a practical example, let's wrap up by discussing some common mistakes to avoid so you don't lose marks on these types of problems. First, be careful not to ignore the square matrix rule. A very frequent error is attempting to identify a diagonal matrix within a non-square matrix, for instance, a 2x3 matrix. As we established in our introduction and during our step-by-step example, the very first requirement is that the matrix must be square. If the number of rows does not equal the number of columns, it simply cannot be a diagonal matrix. Second, avoid the assumption that the elements on the main diagonal, such as a sub 1-1 or a sub 2-2, must be non-zero. This is a common misconception. As we noted in the mathematical definition, the diagonal elements can be any value at all. In fact, a 0 matrix, where every single entry is 0, is technically a diagonal matrix because it satisfies the primary condition. All elements outside the main diagonal are 0. Finally, do not confuse a diagonal matrix with a scalar matrix. While it is true that all scalar matrices are diagonal matrices, the reverse is not necessarily true. To be a diagonal matrix, you only need to ensure that the non-diagonal elements are 0. There is no requirement for the elements on the main diagonal to be equal to one another. They can all be different, which is what distinguishes a general diagonal matrix from a scalar one.